Okay gang, next up is going to be practical skills, which we are going to go over and over and over all year long, and if experience tells me anything, you're probably going to hate this stuff. So you may want to watch this one a couple times just to make sure it really goes in. There is a lot to remember. None of it's too complicated, it's just remembering it seems to be an issue for folk. So some of this you already know. So we'll start with results tables. In your exam, you can be asked to draw or complete results tables, and there are expectations on how these should be done. This is an example of quite a good one. So the reason it's good is because it's got clear headings, so it tells you what the quantity is, and it shows you what the units are as well. So the units are separated from the quantities, and they should always be shown. So for instance, you can see that potential difference is in volts, current is in amps. Now I don't really mind how you separate it. Sometimes folk put them in brackets, that's fine. I will always use the slash like it is on here. Right, so other things. Everything is recorded. All your raw data needs to be recorded. You don't just put the average. You've got to put everything down. Correct significant figures should be used. Right, you're going to hate this, but here goes. So, if it is a recorded value, so something you've measured, you need to write down all the significant figures that you can from your measurement. So for instance, with this one, we would have used an ammeter, so you just write down everything that's on the ammeter. Now, for the calculated value, the average, it has to have the same number of significant figures as the smallest number that was used to calculate it. So here it's easy, because all my currents are to 2 significant figures, so my average should be to 2 significant figures. If one of them had been to 3 significant figures and the others were 2 significant figures, then I would choose to use 2 significant figures for my final answer. And that's the same with any value you calculate at any point in the exam. Generally, if you're not sure, put either 2 or 3 significant figures, but that is the rule, that we use the smallest number in the values that we use to calculate it is how many we use to write your final answer. So let's check we know what significant figures are. All non-zero digits are significant. Zeros are only significant if they have non-zero digits on their left. So there are some examples of significant zeros. So the ones that are red are significant, the ones that are black are not. And it's pretty straightforward. As long as a non-zero number came first, then you count all the digits that come after. So often we need to think about how many significant figures we're going to write numbers to. So here is a number, 3250.040. So that is 7 significant figures. If I was going to write it to 6, it looks like that. 5 looks like that. 4 looks like that. Don't be tempted to think that that is 3 significant figures, because it's not. Because I know that there were more numbers and I've rounded it, so that is 4 significant figures. 3 significant figures would be 325 times 10 to the 1, or 3.25 times 10 to the 3. It doesn't matter, I've got 3 significant figures, the power of 10 doesn't really matter. 2 significant figures, again, I've got a couple options. 1 significant figure, really it's only going to be 3 times 10 to the 3. If I wrote 3,000, that would be 4 significant figures. Got to watch that one, people do that a lot. You think that you're putting it to 1 significant figure, but you're just rounding it to the nearest 1,000, which is not quite the same thing, so just be careful on that. And if you're asked for no significant figures, then basically you're giving the order of magnitude, which basically just means that you give the power of 10. So in this case it would be 10 to the 3, which tells you how big the number is. That's about all that we need. So that's significant figures. We will talk about this endlessly, I assure you. Okay, graphs then. So graphs we're going to draw a lot because they're useful. They help us see relationships between values. Little note, if you're asked to plot something against something, then the first thing goes on the y-axis. So if you're asked to plot bananas against apples, then bananas go on the y, apples go on the x. So if you're asked to plot voltage against current, voltage goes on the y-axis, current goes on the x-axis. It's just a convention, so you know which way around you're plotting things. So when we draw graphs, we need to make sure that we label our axes again with the quantity in the unit. So here I've got length of spring in centimetres and force in newtons. Should have a sensible scale. Again, you can be asked to draw graphs, so you could be asked to put a scale on them. Sensible scales are 1 to 1, 1 to 2, 1 to 5. So, for instance, 1 centimetre equals 1 Newton, or 1 centimetre equals 2 newtons, or 1 centimetre equals 5 newtons. So those are sensible scales. Do not ever, ever, ever use 1 to 3, 1 to 4, 1 to 6, 1 to 7 is pretty pants as well. If you cannot easily figure out what a value is on the graph, it's probably because it's a bad scale. So you need to be very careful with it. Stick with 1 to 1, 1 to 2, 1 to 5. 1 to 10 is fine as well. Those sorts of ones that are easy to calculate and figure out. You don't have to show the origin, that's the other thing. If you don't show the origin, you can put a zag in. That's the little wiggly thing that goes across the scale. Or you can just label that this is where I'm starting from. You don't actually need the zag. Right, as far as using the paper, this is my favourite thing. You actually get a mark for how much the paper that you use when you're drawing graphs from scratch. And the point is that it has to take up half of the available graph paper. So the way we figure this out is we look at where's my first point on the left-hand side, where's my last point on the right-hand side, and then measure the distance from one to the other. And that has to be at least half the page. Then we do the same from the bottommost point to the topmost point, and again check that that is half the page at least. So that is a good graph. This, which I'm going to see so much of, is a bad graph. And this, which I will also see far too much of this year, is a terrible, terrible graph. It's just awful. I mean, just look at that. What a waste of paper. Remember, you want to pick your scale so that your points take up all the space possible. It's not the scale that you've labelled, it's the points that you are plotting that we care about. Okay, so that was the awful one. So next thing up is drawing a line of best fit. As a note, best fit lines can be curves. However, in first year, you're mostly only going to meet straight lines. We probably won't meet many curves until second year, just because curves are a little bit more complicated. But do know, a best fit line can be a curve. Line does not mean straight line, it just means a single unbroken line. So when you're drawing a line of best fit, a couple of rules of thumb. You need to draw the line so that they're roughly the same number of points above and below your line of best fit. So let's show you some examples. This line of best fit is too high, so it's not acceptable because you can see all the points below. This one is not acceptable because all the points are above it, so it is too low. This one's too steep because you can see that it's further away from the ones at the top and the bottom than it is the ones in the middle, so it's clearly too steep, and here we've just gone the other way, it's too shallow. That is the correct line of best fit, and that is how fussy I am going to be. You'll get it once you've got the practice, you'll understand, but this is what we're looking for, so you're going to be really careful when you draw these, because the gradient will always mean something, so it matters how we draw it, because if you draw it badly, you're introducing error into your calculations, so we have to be careful with these. If you do have anomalous points, like the brown one that I've put on there, you would just choose to ignore it when it comes to drawing a line of best fit. However, if you're actually doing a practical and you get an anomalous point, my advice is go back and remeasure it. Find out what is it really a bad point, or is it something interesting I need to look at? You may as well get the correct data while you can. So if you're doing a practical in class and you get a point like that, just go back and have another look at it. Okay? Right, measuring gradients. I hope we all know how to do this anyway. So to measure a gradient, it's just the change in y over the change in x. And when you're doing these, you want at least each side of the triangle to be 8 centimetres long. Or another way to think about it is that the hypotenuse of the triangle should be at least 2/3 the length of the line that you drew. Basically, draw a big triangle. The bigger it is, the more accurate your answer will be. And we'll talk about that in a minute because you'll have less uncertainty in it. So, big triangles, basically. Right, and your gradient will have a unit as well, and it will just depend on what you plotted on your axes. So, when we calculate the gradient, you can see that we do change in y over change in x. So my unit will be whatever the unit of y is, divided by the unit of x. So that's all you need to do to figure out the unit of your gradient. Easy peasy. Right, I'm assuming you all know what the equation of a straight line is. You're all saying it in your head already before it appears that it is y equals mx plus c, where m is your gradient and c is your y-intercept. Just in case you ever need it, the x-intercept is also minus c over m, so you can get that as well. We're never going to use it, but, you know, completion, knowing more, it's a good thing. So this equation is very useful because it allows us to calculate the y-intercept even if we can't see it on our graph. So this graph, I can't just read off the y-intercept because I haven't got the origin. So what I can do is I can find out what the gradient is. So in this case it'd be 1.5 just by using the numbers that are on there. I then pick some coordinates, so let's say 12 and 16. I substitute all those values into y equals mx plus c, which gives me 16 equals 1.5 times 12 plus c. Then I just solve for c, and that gives me the y-intercept as being minus 2. Now again, the y-intercept will often mean something, so it's useful to be able to calculate it. Okay, this is all the stuff so far. Most of this I would expect you to already know. The next stuff might be a little bit new. So first up becomes some definitions for some key terms. So we'll start with precision. So if we're talking about precision and being precise, a precise measurement is one that has the most significant figures possible. So instead of measuring the desk and saying it's 1 meter long, a more precise measurement would be to say that it was 1 meter, 27 centimeters and 3 millimeters. There are more significant figures there, so it's a more precise measurement. And obviously the way we get a more precise measurement is by having a more sensitive measuring instrument, so one that can measure to smaller values. If I want to say how precise a measuring instrument is, its precision is equal to the smallest non-zero reading that can be obtained. So if we look at your ruler, for instance, you'd probably say it would be 1 millimeter would be its precision, because that's the smallest non-zero value you can measure from it. You could argue that it might be half a millimeter, because you could say it was halfway between the two divisions, and that's acceptable, but personally I think 1 millimeter is probably more realistic. Okay, so there we go. Plus or minus 1 millimeter. If we look at a multimeter that's set at 20 milliamps, we'd say its precision was plus or minus 0.01 milliamps. Don't worry, you'll get the hang of multimeters. You'll have lots of practice with Liam. Or I could pick a setting of 200 milliamps, and in that case my precision is less because I only measured plus or minus 0.1 milliamps. Okay, next up then is accuracy. So accurate measurements are ones that are just close to the true value. That's all I mean with accuracy. It doesn't matter how many figures there are, it's just whether or not it's close to being correct. You get good, accurate measurements by having good technique and good measuring devices and not having any errors in your measurements. So, for instance, if we know the temperature is 20 degrees C, 19 degrees C is more accurate than 23 degrees C. Really easy, right? We will check that you got these terms in your head before too long. Right. Another one that I pretty much guarantee you all have the wrong definition for in your head. If I say something that is directly proportional, or in fact even if I just say it's proportional, I mean something very, very precise. I mean that if I were to plot a graph of them, they would make a straight line, but that straight line would go through the origin. So basically what it says is that if two things are directly proportional, if one is doubled, the other is doubled. And very importantly, if you plot a graph, it would be a straight line that passes through the origin. It has to have both those things to actually be proportional. Most of you would just say it would be a straight line, but it has got to go through the origin, otherwise it is not proportional. It's a linear relationship, but it's not a proportional relationship. It's just about being precise with use of language here. So generally we'd say that it would have the equation y equals mx because c is 0. And you don't always have to write the word direct. If you're told something's proportionate, you assume it is directly proportionate unless you're told otherwise. I hope that makes sense. Okay, uncertainty then. We're getting close. I know this is a longer video, but we're getting close, I promise. So uncertainty. This is something I'm going to look at that's a way of considering how good your measurements are. What's your range of certainty? So, for instance, if I measure how long it takes someone to run a race, the limits are going to depend on how good my stopwatch is. So there's sort of a plus or minus on either side. So if I say they did it in 10 seconds, it could be plus or minus 1 second either way, if I'm not very good, or it could be 1 millisecond either way. So when we're talking about uncertainty, that's what we're talking about. So we need to be able to calculate these. So there's a couple of different ways of doing it. If we have a single reading, so I've just measured something once, or if I did repeats and they were all the same, the uncertainty comes from the thing that we measured with. So the uncertainty, which can also sometimes be called the probable error, in that case it is equal to the precision of the instrument that we measured. So remember how I said the precision is the smallest non-zero value you can measure with the device? Well, if I've just measured one thing, then that precision is also my uncertainty in that measurement. So when I measure the length of my notebook, it will be plus or minus 1 millimeter, because that's how much I could be out by because of the measuring device. So if we look at the scale opposite, it would probably be plus or minus 0.1 without the magnifying glass, because you can see the smallest division is 0.1, so 2 to 2.5, and there's 5 divisions, so that would be the precision of this device. Now if I use a magnifying glass, I probably can be a bit more precise, so I could argue that it would be plus or minus 0.02 maybe. Generally, you don't have to worry about magnifying glasses too much. If you just said that it was this one, you would be correct. Right. Saying that I'm uncertain by plus or minus 1 millimeter. That's useful, but not as useful as it could be. Because, does it matter? Does that 1 millimeter matter? How important is it? The thing that tells me how important it is finding what the percentage uncertainty is. So if I'm measuring something that's 2 millimeters long, being out by 1 millimeter matters a lot. If I'm measuring something that's 10 kilometers long and I'm out by a millimeter, well, I don't really care. That really does not matter. So the percentage uncertainty would give me that feeling of how much it matters. So to calculate percentage uncertainty is pretty easy really. What I do is I read the value on the meter. So if we look at this one, that's 12.6. Smallest division is 0.2, so that's the precision. So in this case, my percentage uncertainty would be the uncertainty divided by the value I measured. So 0.2 divided by 12.6 times 100, which gives me 1.6%. So that doesn't really matter too much. I'm quite happy with that as a percentage uncertainty. If it had been 16%, I would have been bothered. So, as a general rule, to find percentage uncertainty, you do uncertainty divided by the average value times 100. So, for instance, if I've got something that is 45 grams plus or minus 2 grams, to calculate the percentage uncertainty, I do 2 over 45 times 100, which gives me 4.44%. Easy peasy. Now, sometimes, if I have taken a couple of measurements, then calculated a value I'm interested in from those measurements, well, I need to figure out what the uncertainty in my calculated value is. And it's going to depend on the uncertainty in the measured values. So I would do that by combining the measured values. So for instance, if I multiplied my two measured values together, what I would do is I would add the percentage uncertainties together to find out the uncertainty in the calculated value. So, an example will probably help here. If I want to know the uncertainty in a force causing a mass of 50 kilograms, that's plus or minus 10%, to accelerate by 20 meters per second, which is plus or minus 5%, well, I'd calculate the force by doing mass times acceleration. So I'm going to be multiplying the mass by the acceleration. So if I want to find the uncertainty in my calculated value, I need to add the uncertainties, the percentage uncertainties this is, of the mass and the acceleration, the two values I'm multiplying together. So in this case, 50 times 20 is 1,000, and my uncertainty becomes 15% because I take the 10% from the mass and I add it to the 5% from the acceleration. Okay? If you got that one, the rest go easy. So next up we've got if I divide them together, well again I just add the percentage uncertainties. So here I want to find the density. I've got mass and I've got volume. Well, density, I hope you remember, is mass divided by volume. So that means I'm going to do 300 divided by 60. So the uncertainties, which are 5 and 2, all I'm going to do is add them together, which gives me my 7% that I've got here. Okay, hopefully this is starting to make a little bit of sense. Next up, we've got powers. So if I raise something to a power, so for instance pi r squared, I measured the radius, then I squared the radius. Well, in that case, what I do is I multiply the percentage uncertainty by the power I raised it to. So let's look at an example. If I've got the volume of a cube, and I measured the side to be 4 centimetres plus or minus 2%, well, to find the volume, I'm going to do the length of the side cubed, so I'm going to take the uncertainty and multiply it by 3, which will give me 6%. Okay? Right, we're nearly there, I promise. Next up, we've got uncertainties in gradients. So if I want to find the uncertainty in the gradient, what I have to do is draw a second gradient. So my points that are plotted are set, but the gradient was it was something that was my best guess of where the gradient should be, because that's why it's called the line of best fit. But it could have shifted slightly. It could be slightly shallower, it could be slightly steeper, while still being within the range of those points. So what we're going to do is we're going to put on a line that still matches those points, but is the worst it could possibly be while still being acceptable. Now, as far as your exam goes, what I'm going to tell you to do is you put the ruler on through the line of best fit and nudge it a tiny bit, so it's just tilted one way or the other. And that's how you put your line of best fit on, your worst line of best fit on. In reality, what we would do is we'd look at the error bars. So we look at the uncertainties in the measurements, and we put well, it could be this much above, so you put the line that goes up, let's see this camera, a little bit that goes up, and a little bit goes down. So you get the sort of the, so it's that shape there. In fact, give me a second, it looks like, probably seen one of these before, so like that. So if my point is here, I can say, well, it could be this much above or this much below. And that's your error bar. So when you draw your line of best fit, it still needs to go between the error bars of all your points, which is a technicality, because as I said, if you just nudge it slightly, that will be acceptable for the exam. So then once you've got your worst line on, you find the gradient of your worst line, and then the uncertainty becomes the gradient of the best line minus the gradient of the worst line, which you then put over the gradient of the best line. So the reminder is best minus worst over best times 100. And we can do exactly the same for the y-intercept. So we put our worst acceptable line on, we find the y-intercept from the worst line, we do the y-intercept of the best line minus the y-intercept of the worst line, and we put it over the y-intercept of the best line times it by 100. So best minus worst over best. Okay, I'm going to stop here because I know I've given you a lot of information. Hopefully most of it feels alright. It'll be the later stuff that I know you probably won't like, the uncertainties things. We are going to practice them a lot, and we're going to practice them pretty much every time you do a practical, you'll practice some of these skills. So I know I've given you a lot of information. Don't panic. We will practice it and you will get it. But it's important to start thinking about these things every time you're doing a practical now. Okay, so remember, if you've got any questions, you just need to ask me when you see me. I expect you probably will from this one, because there was a lot of information to get into your heads. Okay, and I will see you in your next session.